We're starting at example 6 on the product rule and quotient rule packet. In this example, we've been giving a set of data that inputs the price of each trinket and outputs the number of trinkets they sell when charging that price. Part A says that we first want to find a best fit model. We're going to call the model T of P, where P is the price and T of P is the number sold. It does tell us to assume that there is a price that would cause the sales to drop to zero. So that would mean if we take this input up high enough that we're going to get an output of zero. So the first thing I'm going to do is I'm going to put this data in Excel, and I have done that over here in cells A1 through B5. The next thing I'm going to do is I'm going to create a quick input-output graph, a little scatter plot. There it is. And what I see here is a decreasing graph, and I also see that it's concave up a little bit, right? It's not linear. I would say it's decreasing concave up. Now we have this decreasing concave up graph. That means it could be exponential or maybe logarithmic. The fact that they tell us in the problem to assume that there is a price that would cause sales to drop to zero means that we need to assume that our function will hit the x-axis. That means we need to choose a logarithmic function. Remember, an exponential function will never hit the x-axis, but a log function will hit the x-axis. So I click on one of the data points, right-click, and add a trend line. I'm going to select a logarithmic function and make sure it displays the equation on the chart. I'm going to just pull this equation up here. It says to please make sure that your parameters are rounded to at least 3 decimal places. So I'm going to format my trend line label and go to number, and I'll take those decimal places out, about 3 places there. There we go. All right, so we see we have a function here, this logarithmic function where we input the price of each trinket and output the number sold. So it's given, of course, on the Excel file with Y's and X's, but we need to change those over to input P, output T of P, revenue equals number sold times price per item. So revenue is number of sold, which is T of P, times price per item, which is P. So we can now say that the function R of P is this T of P function, the logarithmic function we found using Excel. Put that in parentheses, that whole function times P. I'm going to go ahead and just simplify that one step here. I'm going to distribute the P to each term. We've got this first term with the negative 11,000 ln and then we have this second term, which is just the constant. So when we distribute the P, we'll get a negative 11,898.337 P times ln of P plus the 24,130.264 times P. So there is our revenue function. Next, I'm going to take the model for revenue that we've created here, and I'm going to create an input-output table for it. I'm going to go ahead and, start it at 1, and then we'll do $1.50 and 2 and $2.50, just inserting a few values. I selected these because I see in Part C it does ask us to find the revenue at $1.50, so I'll just make sure that's in my table. Revenue function equals negative 11,898.337 times the P times ln of P plus 24,130.264 times the P, and drag that down. All right, it also then asks us to find the derivative and evaluate the derivative function. So I need to find r prime of p. First, notice that my r of p function has two terms. I need to find the derivative of the first term, the negative 11,898.337 p ln p, and then I'll have to add that to the derivative of the second term. So the first term, I have it highlighted here. Notice the first term is a product. I've got negative 11,898.337p. I'm going to change that to red. That's one function, times ln of p, which is a different function. It's like f of x times g of x. To find the derivative of that, I'm going to have to do my product rule. F prime g plus f g prime. So inside this first little parenthesis here, I have to find the derivative of the red function. The derivative of that red function is negative 11,898.337. Then I multiply it times the original blue function, ln of p. So there's f prime g. Now I have to add to it f g prime. F is the original red function, negative 11,898.337 p. And now I have to multiply that times g prime, the derivative of the blue function. So the derivative of ln of p is 1 over p. That's the derivative of the first term, this red and blue term over here. I also need to add to that the derivative of this second term, the 24,130.264p. The derivative of that is just 24,130.264. This can be simplified. This gigantic r prime of p function can be simplified. Notice that the p in the numerator here cancels with the p in the denominator here. So I have now negative 11,898.337 times ln of p minus 11,898.337, and the p times 1 over p canceled out, plus 24,130.264. Finally, I could do one more simplification. R prime of p. These two constant term values can be added together. 12,231.927. And so r prime of p is negative 11,898.337 times ln of p plus 12,231.927. I'll put that in bright yellow there. All right, and I'm going to add that to my input-output table. It equals, the r prime of p equals negative 11,898.337 times ln of p plus 12,231.927. Drag that down. All right, now we have our input-output table. So in my table, I see that r of 1.5 is 28,958.86, and r prime of 1.5 is 7,407.57. At a price of $1.50 per trinket, the revenue is $28,958.86, and at that price of $1.50 a trinket, if they raise the price by $1, the revenue would increase by $7,407.57. It also asks us to do the same thing for a price of $4.50 per trinket. So we see if we add $4.50 to our table, we see R of 4.5 is 28,054.1, so that means at a price of $4.50 per trinket, the revenue is $28,054.10. And at a price of $4.50, if they were to raise the price by $1, the revenue would decrease by $5,664.09.